In field theory, we study the different ways that we can extend the rational numbers. Field theory is largely motivated by our love of solving equations. One of my favorite results is called the Primitive Element Theorem, which says that many of the complicated extensions of the rationals can be generated by a single element. Now, the rest of this video is about what the hell that even means. We'll consider some of the history for context, and we'll cover the basics of what a field is. And to better understand the primitive element theorem, we'll work through an example that's more complicated than one you'll find in a textbook, and I'll show you some tools that'll make the calculations pretty easy. In a college algebra class, you learn a little about the hierarchy of number systems, that the rational numbers are part of the real numbers, and these are both part of the complex numbers. The number systems are examples of fields, which are algebraic structures where the usual rules for addition, subtraction, multiplication, and division hold. Field theory gives us a language to describe ways that we can extend the rational numbers, say by introducing some non-rational root of a polynomial like I, or by introducing an infinite amount of non-rational elements to the rational numbers, such as the jump from the rational numbers to the real numbers or to the complex numbers. We'll call an extension of the rationals simple when we've introduced just one non-rational element, such as in this diagram toward the bottom with cube root of 2, or on the other side with I. The primitive element theorem says that introducing any finite number of non-rational roots is in fact a simple extension of the rationals. As a student, that was hard for me to wrap my head around, and as a professor, that's hard for my students to wrap their heads around. Let's take a few minutes to get some more context for where the ideas in field theory come from and to meet some of the people along the way. Now, our story ends here in 1910 with Steinitz, who proved the modern form of the primitive element theorem. But the driver for field theory is the millennia-old problem of solving equations. As far back as 2000 BC, it's known that the Babylonians had a way to solve certain quadratic equations where the leading term was 1. Fast forward to the 700s AD, when Indian mathematician Brahmagupta discovered the quadratic formula for solving quadratic equations, but he had nothing to do with memorizing it to the tune of Pop Goes the Weasel. Now that solutions to quadratic equations were fully characterized, mathematicians turned their attention to cubic equations. In the 1500s, 3 Italian mathematicians, Del Faro, Tartaglia, and Cardano, independently contributed to solving the general cubic equation. About 100 years later, French mathematician Fermat conjectured what is known as Fermat's last theorem. This problem was largely responsible for the evolution of ideas in number theory. Its proof was finally achieved in the 1990s by Andrew Wiles, and this is possibly the largest success of the mathematical theory of everything known as the Langlands program. Among the many things German mathematician Gauss did, he studied the complex numbers that have integer coordinates, from which he obtained information about factoring that aided mathematicians' quest to prove Fermat's last theorem. In the 1830s, French mathematician Galois developed a theory that was later used to prove that polynomial equations of degree 5 or higher could not be solved via formulas similar to Brahmagupta's or the Italians. In the 1840s, German mathematician Kummer studied the cyclotomic extensions of the rationals and further developed the theory of factorization in the direction of Fermat's last theorem. In 1853, German mathematician Kronecker conjectured that particularly nice extensions of the rationals could be embedded in a simple extension of the rationals. His proof was flawed, but the conjecture was worked on for about the next 40 years. In the 1870s, German mathematician Dedekind developed the theory of ideals. This is the modern framework for studying factorizations and extensions of the rationals, and more generally in structures called rings. In 1886, German mathematician Weber published a partial proof of Kronecker's theorem from some 40 years earlier. It too was incomplete due to an error, but that error was corrected about 100 years later in the 1980s. In 1896, German mathematician Hilbert finally published the first complete proof of Kronecker's theorem, establishing that nice field extensions of the rationals could be embedded in a simple extension. And finally, we're back to 1910, when German mathematician Steinitz proved that all finite extensions of the rationals are in fact simple. So by the theorem, there should be some non-rational element gamma that extends the rational numbers in the same way that the cube root of 2 and the cube root of 3 would extend the rational numbers. In particular, this means that the cube root of 2 and the cube root of 3 could both be written as a sum of powers of a single element. This is the part that's maybe hard to wrap your head around. Let's make sure we understand what elements in this extension q adjoin cube root of 2 and cube root of 3 look like. The notation suggests that you definitely get the rationals, cube root of 2 and the cube root of 3, but we have to let these things interact with each other via the normal rules of algebra. Let's observe some of what I'll call the interesting elements of this set R. You get 1, the cube root of 2 and 4, of 3 and 9, of 6, 12, 18, and 36. The next thing I want to convince you of is that any way you could multiply these 9 elements just simplifies to a fraction times one of those 9 elements. I'm trying to suggest that modulo multiplication by a rational number, these are the distinct cube roots that should be in this field. In other words, no matter how you multiply and you simplify that cube root, you're just going to get one of these options underneath the cube root. The next thing we'll do is we'll study if taking integer powers of any of these 9 elements results in something new under that cube root. This covers the case for division too. Remember, dividing is the same thing as multiplying by the reciprocal, and we're concerned with doing that since this is a field after all. Now we'll begin simplifying each of these powers of these cube roots. Observe that every time, it's one of the same numbers that's underneath the cube root. So if you take any integer power of one of these 9 interesting elements, you just get a rational multiple of one of those 9 elements back. Since we can add in a field, any element in this extension of the rationals looks like a sum of rational multiples of these 9 elements. Another way to say that is that this field is a 9-dimensional vector space over the rationals, and these 9 elements form a basis. Observe that each basis vector is a power or product of the cube root of 2 and the cube root of 3. What we're going to do is we're going to change basis so that each basis vector is a power of a single element called the primitive element. And I'm going to demonstrate to you that the primitive element we could use is obtained just by adding the cube root of 2 to the cube root of 3. I'm going to demonstrate how to do this change of basis using Sage. It makes the computations way easier. So how do we tell Sage to do arithmetic in this field extension of the rationals? What we'll do is we'll say alpha is the cube root of 2 and beta is the cube root of 3, and then we'll rewrite the other basis vectors as multiples of powers of alpha and beta. We're going to tell Sage that alpha symbolically represents the solution to the equation x cubed equals 2. Now if you rearrange that equation, we obtain what's called the minimal polynomial of the cube root of 2. The minimal polynomial is important in a more detailed construction of this extension that I've given to you here. The next thing we'll do is we'll extend our extension by beta, which represents the cube root of 3. This double extension is the same thing as our field generated by each of these 2 elements. Now that Sage knows what alpha and beta are, we can define gamma, which is the sum of alpha with beta. This is the main reason why I wanted to use the computer to do this, is because computing these powers of gamma would be awful. We're going to raise it to the 9th power. But the computer can do this very quickly. In a moment, we'll have the computer print out the outputs that shows us the powers of gamma in terms of these multiples of alpha and beta. Here are those equations from Sage, but a little bit prettier. We should think of this as a system of equations. Let's keep these up here for a moment. Let's rewrite this system in matrix form, where each column of the matrix represents the coefficients of one of the green basis vectors. And just so we're all on the same page, the equation alpha plus beta equals gamma is the result of the matrix multiplication at this step. We'll do a few more of these slowly in case you really want to track that these coefficients are going in the right place. But if you're feeling pretty good about this stuff, feel free to fast forward about 20 seconds from now, when this matrix equation will be complete. Alright friends, we made it. So, this matrix that we end up with, it's invertible. You could check that its reduced row echelon form is just the identity matrix. That's pretty great because then we could try to solve it just like any linear equation. We just want to undo that a on both sides. So we can multiply both sides by a inverse. We'll use Sage to compute the inverse of a. It's a pretty simple command too. It's just a to the minus first power. And boom, here are the entries of the matrix A inverse. We'll substitute that in. This matrix equation is exactly what we needed. If we look at the second and fourth rows, this tells us how alpha and beta can be written as linear combinations of the powers of gamma. In other words, now we know how the cube root of 2 and the cube root of 3 can each be written as sums of powers of a single element, cube root of 2 plus the cube root of 3. All right, so let's wrap this up. We have shown that these two extensions, they have each other's generators. That means that they must be the same extension of the rationals. Pretty simple, huh? Thanks for watching.